This ODE looks even worse, and it has some interesting behavior. We can't solve for it except in actually one case, but here's the idea here. So right, this is f of x comma y. So f of x comma y, it has a problem, I'll say. Has a problem. Oops. At x comma y is equal to 0, 0. I said it has a problem because it's kind of a weird case. So, right, if we can get a division by 0 in this, but in order to get a division, by 0, we have to have x is 0 and y is 0. But then we have 0 squared minus 0 squared on the top, which is 0. We have 0 squared plus 0 squared on the bottom. So we get 0 over 0. So that's kind of weird. All right. So it looks like we're not guaranteed a solution exists when we're at the origin. Not completely sure about that. It's a little weird case. I'm not going to compute partial f partial y, but it has the same problem. So, right, it doesn't know about the origin. But the rest of it is just fine. So partial f, partial y, has the same problem. So the only way to really investigate this, we can't solve it. The only way to investigate it is to have a computer plot some solutions for us, at least approximate solutions. So if you do that, and I'm going to actually draw this one as like a box. So here we'll have, a -5, -5. This will be 5, 5. And so, right, the origin's in the middle here. So what this ends up looking like is it makes these sort of bumps. So I'm going to draw the origin, right there, let's say, and it makes these weird bumps. So if I come from this way, we have a line going here, it goes this way, and it'll kind of make a bump, and it'll go back down. But then if I'm a little, farther away, it makes a bigger bump. And then if I get really, really close, you can make a tiny bump, and it goes back down. And then it's kind of the opposite in the other direction. So in the other direction, I'll kind of do this backwards. So you make, a little bump, and then it goes that way. But then if you're a little further, it's going to make a larger bump, and then it goes. Then you go a little further, and it makes an even bigger bump. And I didn't draw that one very well, but the bumps get really, really big. But the thing is, you can't really get a solution going through this point. Where is there a flat line in between all of these? Because these curves kind of fill the entire square if you keep making them. But the only point it doesn't seem to be going through is some line. So what I did is I thought, okay, well, maybe I can come up with one solution to this. So what if I have a line that goes through the origin, like that? And then I looked at that line, and I said the slope, m, is approximately 0.5. It looks like it's a little bit larger. It's kind of blocked in by all these other curves. So then I thought to myself, okay, what if I try, what if I make a guess? So sometimes you can guess a solution. In this case, I was able to guess and it worked. So I'm going to guess a solution y of x is equal to mx. I don't know what m is, but I'm thinking there's a solution like that, I'm hoping. So what ends up happening is you have y prime, right, then is going to equal just m. And in this equation, we're going to end up with y prime on one side, so we end up with m equals, we have x squared minus y squared, so x squared, but then y squared was mx, so I have a minus m squared x squared. On the bottom, I've got x squared plus m squared x squared. And it turns out, I don't think you can actually solve this yourself. It ends up being a pretty terrible equation. Maybe you can, I'm not sure. But I just had a Wolfram Alpha do an approximation for me. Turns out m, to solve this equation, is approximately 0.54369. And so, yeah, right, I said, m is about a half, but a little bit bigger, just looking at the plots that a computer did. And it looks like, to solve this equation, to magical value of m is the 0.54369 approximately. And so this one came out a little more interesting. There was this potential problem at the origin, but it turned out every single point in, everywhere, every single initial condition, x naught, y naught, including the origin, ended up having a solution. And so this is a little bit different from all the other ones, so the existence uniqueness theorem said, you're good everywhere except if you go through the origin, if you start at the origin. And it turned out if you start at the origin, you actually do just fine. So there's actually, it looks like, a unique solution for every single initial condition, even though the existence uniqueness theorem said there might be some problems.